gravity is, well, we had the introduction already, so let's just jump right on in. So the universal law of gravity, the force of gravity turns out there's some basic properties. That the force of gravity, Fg, it's proportional to the product of the masses. So it's proportional to not just one mass and each of the masses, it's both masses. And you know what gravity is, right? Like if you consider the third law, let's say that we have a mass 1 and a mass 2. When there's an accumulation of mass, there's an attractive force called gravity that applies to other objects. So mass 2 will apply force to mass 1 that acts along the center of both masses, actually. So, and this is the force of mass 2 on 1. That is the terminology that we use. And there's an equal and opposite force on mass 2 due to mass 1. That we'll call force of mass 1 on 2. And what we say is that F12 equals the negative of F21. So, I mean, that's essentially the third law, right? That's saying that. But that's also an inherent property of gravity, is that it's an attractive force, so that dictates the individual direction of the forces direction of the forces on individual objects. But what I wanted to point out here with this first property is that even though the masses M1 and M2 are not necessarily the same, they do not have to equal one another. They could, but they don't have to. The forces will always equal one another. And that is, it might seem counterintuitive, particularly, if one of these masses is a feather and the other one is a bowling ball, you might not think that the feather actually applies the same gravitational attraction to the bowling ball as the bowling ball attracts to the feather. It seems counterintuitive. But it is this property of the third law that dictates that, because it's not one mass or the other of which the gravitational force is proportional to. Rather, it's the product of both masses. And so that's why that can be true. And it also leads to the third law, because the third law would be violated if that were not the case. So it's really interesting how those two laws work together, and they were proposed at the same time. I think if you notice in that movie, Newton's Principia came out in 3 volumes. I think one was the first volume was the laws of motion, 1, 2, and 3. The second volume was gravity, and the third volume was calculus. So, pretty amazing dude. So property 1, okay. And then another property is that, I guess, is that the, it's an attractive force and it acts, I mean, you can make this 1 or 2 properties. I'm going to combine them. So it's attractive force. And acts along the center of mass of each object. Yeah, I mean, maybe you could make those separate properties. I don't know, but yeah, maybe we could say that. Attractive, acts along the center of mass. Let's do that. But the big one is that also the universal law of gravity is proportional to the inverse square of the distance. That's the big deal. And it's called the inverse square law. And you actually heard Haley comment, or Newton comment on that. It was the first thing that they asked that he, when Haley in that meeting. Because that ultimately gives the, allows you to solve a differential equation that leads to the equations of motion for objects that are experiencing this law, particularly central force objects orbiting orbital motion. And it proves Kepler's law. Like, this leads to the proof that orbital bodies which have a central force orbit in an ellipse, which Kepler had shown previously, but it was empirical data that led to that. But Newton was able to prove it by creating calculus, applying the law, setting up a differential equation, and solving that differential equation. And the solution were ellipses. So it confirmed, it told more than what Kepler had done, but it also confirmed some of the results that Kepler had shown. So when you put all of that together, and I guess you could put in the, the law is proportional to all that, but the constant of proportionality is G, is the, is the universal law, universal gravitational constant. So you put all that stuff together, you get that the force is equal to negative G M1, M2 over R squared, where G is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. No, not negative, positive. Let me look at it real quick. It's gonna have to be positive, right? Not negative. Yeah. Positive. Oh no, I'm sorry, negative 11. 6.67. Yeah, that's it. Okay, now, a couple things about this. This law abides by superposition, so that if you have, say, some mass m0, and you have several other masses, m1, m2, m3, a system of particles, then all of those particles will have their own individual gravitational force on mass m0. And again, acting along a center of mass. So you're going to have that guy, this guy, this guy. So you have F3, F2, F1. So you can superpose all those. The net force, it'd be the summation of all those. It depends on the mass and everything, but like the resultant force might be something like, who knows what, I don't know. It depends on what, how big they are. Now, it could be anything arbitrary, by the way, I'm drawing it, but just arbitrarily, the net force might be that thing. So you have to do a vector analysis, right? What does that mean? That means that you have to go in and apply an axis. So maybe you superimpose an axis like this. This goes back to the vector analysis that we did in the beginning of the class. You superimpose an axis like that. Then you have to put in all the components, right? You're going to have the components of all of those things, meaning like F1, you're going to have an F1x and F1y. So on and so forth. And when you add them all up, you get the resultants. And the resultant along the x direction will be the resultant of the component of your resultant, right? FR x, and then it'll have an FRY, which is going to be the sum of all the y components of the individual particles. And so that's like F3y, and then F2y is here. And so F1y, F2y, F2y, F3y minus F1y is going to be FRY. And then all the X components will add up, right? And so F1X, F2X, F3X is going to be equal to FRX. In fact, I could like kind of knock it out real quick, right? So this is the way I would write that. So here, you have to use superposition principle. So we would say that the net force, F net on M1, is equal to G times M naught times the summation of I equals 1 to N of the M sub i's over the R sub i's squared. You put in a unit vector to represent that. All right. And F then, so that's the net force. But another way that you could write it would be in terms of its vector notation. That is, in 2 dimensions, F net, right, is going to be equal to F R X I plus F R Y J. The magnitude F net then is going to be equal to the square root of F Rx squared plus F Ry squared. And the angle that it makes with respect to, the reference angle, just like all the stuff we did before, the reference angle theta, this guy, theta sub r, that's going to be, well, tangent of theta these equations 1, 2, 3, 4, 5, 6. So tangent of theta equals FRY over FRX. So that theta is equal to FRY, or the inverse tangent of FRY over FRX. Absolute value is what we're using there. So those are all the, basically vector analysis equations that we would apply that we've seen before. All these things are, I'll call that stuff in. So basically, say for a system of discrete masses, for a system of discrete masses, use vector analysis to find the net force on an object. And of course, as I was saying, right, to finish that out, that F, let me do it here. FRX is equal to, in this particular case, it would have been F1. And, they all have their respective angles, right? So like F1 X plus F2 X plus F3 X. and F1x equals F1 cosine theta 1, F2 equals cosine, so on and so forth. And that's just the magnitude. And FRY, in that case, it would have been F1y and then minus F2y and minus F3y, because F2y and F3y are pointing in the negative direction. So, you know, it's vector analysis for discrete, and this is considered a discrete system of masses because the masses are separate from you know, they're not connected. So two particles, a system of particles, and then finally we can talk about a continuous mass distribution. And basically it's the same formula here, but then the summation sign becomes an integral, and the individual masses becomes a differential mass. So for a continuous system, a continuous mass distribution, I guess I have a little space down there, so I can try to get it in. The net force then equals G times MO times the summation. Actually, you know what? I'm running out of space. I think my ink is not so dark. That's really the issue. Let's try. Integral, there you go, of dm over r squared, r hat. So this m sub I becomes a differential mass. R squared is just, you know, r of the differential mass. And the summation is the integral. So that would be like, you know, let's say that I had.
Professor?
Yes.
So when you wrote in the beginning F equals negative G M1 times M2 over R squared, why is it negative? Like, why is there a negative?
That negative sign represents the attractive force. I just erased that property, but gravity is inherently attractive, which means that the force, like here, if this is mass 1 and this is mass 2, then this force represents the force of mass 2 on mass 1, but it points back toward mass 2. And this force represents the force of mass 1 on mass 2, but that force points back toward mass 1.
So the book has this formula without a negative sign? The top?
No, I'm sorry. No. Say again?
The book has the formula without a negative sign, and it has another formula with a negative G, but with R, not R squared.
Yeah, so that's the calculus stuff. So first of all, when it doesn't have a negative sign, it will not have a vector symbol over here. It means it's the magnitude. You can write that a couple ways. You can write it like this: F magnitude equals G M1 M2 over R squared. And so you won't have the minus sign. And the other way that you can do that is, well, if they do the 1 over R, that they should have the minus sign there, because that's the definition of a unit vector. This is a unit vector here, and in calculus, the unit vector is defined as the vector R over, oh my gosh, I'm about to mess it up, R squared. Is that, you're the math person? That's right? That's the definition of a unit vector, right? Is the vector over the magnitude of the vector, right?
Yeah, that's what I remember.
Yeah. So
It has
Right.
those like, it's not the absolute value, but you know those two lines for to show magnitude
Yeah.
in the denominator.
So, because let me see if I can work it out. Because the way you work it out is you do a vector times a vector, right? So that's going to be r. Actually, that's a unit vector. So it's the vector times the vector, which is the magnitude of the vector times the unit, divided into the magnitude of the vector times the unit. So that's going to be r times r, because you can factor it out. So r squared times r hat dot r hat, which is r squared times, and this is the definition of a cosine. And unit vector has magnitude 1. So magnitude 1 times magnitude 1 times the cosine angle between them, but they're parallel, so that's 0. So that's just r squared. So r vector times r vector um, equals r squared. So uh, if I divide through by 1, divide both of these things by r squared, then what I have is r vector times r vector, done r squared equals 1. But that's how, but the magnitude of a unit vector is 1. So I think that's how the definition. Yeah. So I had messed up the previous thing. This is the definition of a unit vector. Yeah, I think so. Um, so that how do I get back to this? Putting that inside here. Um, yeah, so I think I'm overthinking it, but that's just it's just oh right. So what you were asking about was this other notation. The You were asking about, yeah, right. So you're asking about,
So I just wanted to know, like the book has the formula without a negative, and you said without the negative is just the magnitude, and
yes,
with the negative sign it shows the attraction between the
yes,
two masses or particles.
yes.
So
So go ahead.
yeah, because um, so the book has, you know, the formula that you wrote, when the book has it with a negative sign, it has r, not r squared. So that's a different thing.
Yeah, so that's the last thing I want to point out. First off, before I point that out, this thing, sometimes you see it like you can either write it like this with a vector notation in the absolute value, or you can just write F. That's also equal to just F without the vector symbol. If you put the vector symbol and to get the magnitude, you have to put the absolute value, or you could just write it without the vector symbol and it's the same thing. So these two equations, this guy and this guy are equivalent equations. This is another form. This is the form that I like to do it in terms of the unit vector, but there's another form, which is what you're talking about, and it comes out of the definition of, um, I'm trying to figure out how to get to it. It's like, so like a vector, that symbol has a magnitude and a unit vector. Oh, it's just that. It's just that. So that the unit vector is actually equal to the vector divided by the magnitude. That's one way. That's another way to write it. This is one way to write it, the dot product between the two, but this is another way. So I believe, and I'm not looking at it, but I'm guessing that they wrote it in terms of the vector. Because if I take if I split this up, right, look at this. I can take this equation here, and you can tell me if that's what they had. If I write this minus G, then M1, M2, and I can split this up. I can make that R, and then I can make this thing R hat over R. But then, wait a minute, what? Yeah, yeah, what? Wait a minute. Did I write it wrong? No, couldn't have. This is right, isn't it? So
So with the negative, you're saying it's the attraction between the two, right? So is it the same thing like the book is saying, the gravitational potential energy of a system of two particles with masses capital M and small m and separated by a distance r is the negative of the work that would be done by the gravitational force of either particle acting on the other if the separation between the particles were changed from infinite to r. The energy is, and then it gives a formula U equals negative G capital M times small m over r. So is it the same thing like you're saying that it's the attraction of the two gravitational like is it the same concept or is it different?
that's a different concept. I didn't realize what you were talking about. That's energy and potential energy. This is force. Energy and force are not the same thing.
Okay.
So the negative sign is associated with an attractive force. I haven't said anything about the potential energy between the particles, between a system of two
I was just
particles.
asking if this is the same thing, same concept, or is it a different concept?
And I'm answering the question. Force and energy are not the same thing. When you were first asked the question, I thought you were talking about force. I mean, force and energy are not the same thing, right? Like, is potential energy gravitational force? No. Gravitational force is weight, mg. Potential energy from the point of view of Newton's three laws is mg times h. And the quantity energy is very different from force. So I guess I was a little confused. I probably should have looked at what you're talking about, but I thought you were talking about force. And there are various ways to represent the force equation, which is what I'm showing you. But the 1 over r is energy, it's potential energy. And that I will derive that for you, but that's something different. We haven't talked about that yet. So you can't try to make that equation fit this equation. They are related, and I'll show you how they are related. But the short answer to your question is yes. Potential energy is a different concept than force, and that's why the equation is different.
Okay.
So we're more so at the beginning of the chapter where we're talking about force. I haven't talked about potential energy yet.
Okay.
Is that clear? But that
Yeah,
said,
I read the chapter and I was not finding the other formula, that the one you wrote. That's why I'm confused. I'm like, is this the same thing or different thing? So, I mean, I'm sorry for the confusion. I was just trying to understand if it's two different concepts or one. And I understand what you're saying. So, sorry about the disturbance.
oh, it's no disturbance. That's okay. And what the two different formulas are, you mean these things here? These here? The representations you're talking about. Not, hello?
I'm sorry, I kept talking and I was muted.
No, that's all right. Yeah. So they basically just don't show this formula. That's the problem, right? That's what you're saying?
Yeah.
Yeah. So I don't know why people don't do that. I like to do it because it's a vector. And this negative sign, the only thing that it's just, this negative sign just means attractive.
Okay.
It just means attractive. Now, we got to be a little bit careful about the negative sign when we talk about energy. I'll talk about that. But, energy is not a vector. So there can be negative and positive energy, but it has nothing to do with direction. It has everything to do as to whether energy goes into the system when you do work on it, or whether energy comes out of the system when you do work on it. And it gets even a little bit more complicated for orbital bodies, which is what we're really applying this stuff to. And again, I'll talk about that momentarily, but for now, we're just talking about force, and this minus sign does mean direction. And it means that, like right now, you're in class, like you're in front of me. If you were in front of me, we would have gravitational attractions on one another. And if I could visualize the force of my attraction on you, that force would be pointing back toward me. And if you could see the force of attraction on me due to you, it would be pointing from my center of mass back through your center of mass toward you. That's what this minus sign means. It's an attractive force. So,
Okay.
and if there were no other forces holding us, like the friction between the floor and my feet, and maybe if you were sitting at a desk, the friction between you and the desk, if we were up in space somewhere away from those kinds of forces that can retard our motion, we would see that over time, we would start to accelerate toward one another because of the attractive force. That's what this minus sign means.
Okay. I got it. Thank you.
All right. Yeah. Now we could go one step further. I can take this and I can derive the acceleration due to gravity, the constant, show you where it comes from. There's a difference between force and a field. The concept of a field, we kind of use these things up till now. You've probably been using them interchangeably, but technically a gravitational force is different than a gravitational field. In general, the concept of a field is the following. And this was actually, Newton actually didn't he probably knew it, but he didn't write it down. It wasn't really formalized until Michael Faraday with electromagnetism, but you can apply it back to gravity as well. That a field, G, it actually looks almost trivial. Like we say that weight is equal to mg, where a weight is a force and G is, we call it an acceleration because we're really dealing with it in terms of motion and things like that. But if we solve this thing for G, well, first of all, this weight is this. The weight of an object is equal to the gravitational force of the Earth on that object. So replacing W with Fg, gravitational force of an object is, the force of attraction from the center of the earth goes the same thing argument I just made with you. I can make that with the center of the earth, right? It's on my center of mass. It goes through the center of the earth. The force that the earth applies on me, I apply that same force on the earth coming back toward me. Now, if I have an object, I think I might have asked you this in class before, but let me ask you again. Brian, why don't you answer this? Well, actually, first of all, let me solve this for G. That G is equal to Fg over m. So F is the force, and G, I want you to think about it now, not just in terms of a kinematic property, but in terms of a field property or a concept of a field. And I can describe to you what that, give you an intuitive understanding of what that is. G is a field vector, not just an acceleration vector, meaning a kinematic quantity. So G is a field vector, full stop. Its properties extend with properties that extend beyond, full stop. Its properties extend beyond kinematics and motion. One of the ways I can start to explain that is the following. It's true that when we drop this object, what is its acceleration going to be? Brian, what's the value of its acceleration?
It's 9.8.
9.81 meters per second squared. And that's the magnitude of G. So that's how we've been thinking about it. Remember, perspective is one of the proper themes of this course. So I'm simply going to have you, I'm changing
Professor?
Yes.
Yeah, I just want to make an observation. Is this what makes the difference for G to change in a different planet?
It's related to that, yes. And we're going to show you, in fact, yeah, it's related. And I'll show you how you basically what I'm leading to is going to derive a formula to show you how to calculate it for different planets. But yes, it is very much related to that, yeah.
Okay, thank you.
So yeah, so what is a field? So the motion of this particle, yeah, the acceleration is 9.81 meters per second. So because we focus so much on thinking about this with regard to motion, we specifically associated that quantity with this object and its motion. Now, when I have an object here in this space, and I could measure the mass of this object, and I could ask you, is there a force on the object? And you clearly would say yes. In fact, that force is what's causing it to accelerate, according to Newton's second law of motion, right? The force is just the weight, m times g, that I wrote right here. And so its acceleration when I drop it, and right now there are two forces on it, the normal force or my tension force, whatever, up, and it's equal and opposite to the weight, which is why it doesn't move. But when I let it go, and when I assume there's no drag forces on it, then the only force is the force of gravity, and it falls with that acceleration. So again, we specifically, because we think of that so much, we're associating the acceleration with the object. Now, let me ask you this. If I take this object away from that space and there's nothing else there, no, assuming a vacuum, no air molecules or anything, Brian, is there a force in that point, P, let's say that field point where that mass was before I removed it? Once I remove it, is there a force in that point? It's not a trick question. Is there? Go ahead.
I'm going to say no.
No. There is no force because there's no object there. That's right. You're absolutely right. But now let me ask you this. Is there an acceleration field at that point, and whose value is 9.81 meters per second squared?
Now for that, I'm gonna say yes.
Well, you would be right if you said that. Yeah, and that is my point. There is an acceleration field there. It's equal to 9.81 meters per second squared. And so what it's really showing is that acceleration of this object, it is the acceleration of the object, but it's not directly associated with that object because it's there even when that object is not. That's what a field is. It's in the area even if the object is not there. And it's manifesting itself when you place an object there because of the relationship between force and mass for an object. But implicitly, it's got to be something different than just associated with the properties of that object. That's the point. That's what a field is. It's there even when other things aren't there. And in fact, one of the reasons that it was defined, you could state that's really a mathematical concept. Is it not? Doesn't really matter. In the end, it's all the same in terms of the way that we handle it. One of the reasons it was defined when we get to electromagnetism, we'll define it, is because it's useful to think about the force on the object as coming from the field around it, as opposed to coming from the object that creates the field. You might not even know what that object is. You might not even know, and it's more obvious when we get to electromagnetism that we can set situations up like that. But it's another way to think about it. It's that the force is actually coming from the field on that object. That field is placing a force on the object, as opposed to thinking about the earth creating a force. In the end, it's just a different perspective to say the same thing, but that different perspective can be very useful. So I want you to start to elevate your thinking, because it's going to help. It's the first thing we're going to do next semester in E&M, is to begin to think about G as not just associated with the motion of objects, but it is actually the gravitational thing. Like when we think about gravity, what we think of, because up till now, you've been trained to think of force, but that's actually not gravity. That force is the result of gravity. Gravity is not the force. Gravity is G. And when we actually draw and use vectors to represent the gravitational field, when you see the earth like that, right? And you have stuff there, whatever. I'm bad at this, right? But, okay, yeah. Sorry. Yeah. I shouldn't go so far. Right. Everything's got to be the biggest thing. So. I don't know. I'm terrible at that. Whatever. So, you're going to look in books and stuff, and they're going to draw. And so what we say, and again, Amna, the negative sign is these lines that are pointing inward toward the earth. So that, again, that's the negative sign. The gravitational field, we say it's radial, and it points in toward the center of the earth. Well, when you see that represented, there's no objects around the earth, right? We usually represent it. I mean, there could be a bunch, but when you represent it, like satellites and stuff, but that's not what these things, like there's nothing there. So clearly that's not representing force. Because as you just said, in order to have a force, there's got to be something there for it to be forced upon. But when we represent a gravitational, gravity, this is how we would illustrate it. So what we're actually illustrating is the G field, G. And what it's actually showing is that G actually isn't constant. We just assume it's constant very close to the earth. But in fact, as you move away from the earth, the gravitational field decreases. How does it decrease? As 1 over r squared. That was one of the properties. Now, it just so happens that the force does that too, right? Because the force is just a constant multiple of that thing. But all of the properties that I just related to you, well, many of them, they are inherently associated with the field, not just the result of that field, the force of that field on an object. So G is also, in fact, in order to get the functional form of G, what we need to do is, this basically is Newton's second law, and the functional form of the force is Newton's universal law. And again, it's the brilliance of the genius of Newton that he actually put those two laws together in order to show us how to calculate G, how to calculate it. And it's done so in this way. If equation 5 then is the universal law of gravity, M, let's call this M naught. So as I just wrote it down, it's, we'll take the magnitude. Deal with that, so I have to deal with the minus sign. So then G, M naught, M, so maybe M is the mass of the Earth and M naught is a satellite or something like that, I don't know, divided by R squared. Well, if we substitute equation 5 into equation 4, look what we get. That G, the magnitude of G, I'll go with the magnitude, equals 1 over M naught times G M naught M over R squared. So that the magnitude of G, so the M naughts cancel. And I get G times M naught, M, capital M, over R squared. So in the case of, and of course it's a vector, so if I wanted to put the vector notation, I could put this back in as well, that guy. So why don't you do me a favor? Why don't you calculate that for the Earth and for the Moon? And you can look up in the back of the book, in your book somewhere, or maybe I can give it to you, the constants. And so the R in this case would be like the radius of the Earth. Right, so like if you had an object on the surface of the Earth, like me standing here, then my mass would cancel out. So my distance away from the center would be the radius of the Earth. So let's calculate that, and you'll see. And so for any planet, if you know the mass and the radius of that planet, then you could calculate the acceleration due to gravity of that. So like, for example, for the Earth, the mass is, we'll do the mass and the radius of the Earth. I'll tell you real quick. And so you can just verify it for yourself and see that that's where these values are coming from. So the radius of the Earth, 6.38 times 10 to the 6. Meters. And the mass is 5.97 times 10 to the 24th. Kilograms. And the moon's mass is 7.35 times 10 to the 22nd. Kilograms. And the moon's radius is 1.74 times 10 to the 6th. Yeah. 1.74 times 10 to the 6th. And then when you calculate G, give me the ratio of G of the moon as compared to G of the Earth. What is that ratio? Actually, do it the other way around. G of the Earth compared to G of the moon. I think it's going to be about, well, you tell me that you figured out. So go ahead and do that as a class exercise right now, please. And why don't you do another exercise? This will be a quick one. So let's calculate the gravitational attraction between two average people. Richie, are you self-conscious? I'm going to tell you my weight and then well, let's approximate our masses. I'm about 80 kilograms. What do you think? Do you know approximately what your mass is? I mean, average.
Yeah, probably 90.
Okay.
90
cool.
to 100 maybe. Yeah.
All right. So as an exercise, once you finish this, go ahead and calculate the gravitational attraction between me and Richie. Like if we were, and we know, because we can compare it to something, right? I know that the gravitational attraction of the Earth on me is about 800 newtons, right? Because I'm about 80 kilograms. And the Earth, the G is about, we know it's going to be about 10, 9.81, but yeah, approximately 10. So that's a little bit less than 800 newtons. Okay, well, we can actually compare that to the gravitational attraction between two people. I'm 90 kilograms, he's 80 kilograms. Just plug it into the formula and figure out how many newtons of attraction is between us. And remember, because of the property of the universal law, doesn't matter that we're different masses, the force of attraction between us is going to be the same because of the Newton's third law of motion. So do that right now as well. I'm going to take this out to 3 significant digits. So I did there. So if you plug that into the formula, and what am I using? 6.67 for G times 10 to the negative 11. Yeah. So what we should get is, let's see here. Yeah. Enter, you just plug it in. So mass. And then the distance, 6.38. Squared. Yeah, well. Did I do that right? No, it's not the radius of the Earth. Radius of the Earth is 5.97. Where did I get that from? What happened? Oh, yeah, wait a minute, hold on. No, the radius of the Earth is, yeah, 6.38. Okay. Yeah, okay. Yeah, so, well, 9.8. Probably at sea level. I don't know what they're doing. It's a little bit off. Yeah, 6.3 times 5.9. So yeah, that's what's the standard radius. Maybe a mean radius is what. Whatever, yeah. So approximately 9.8. I've been using, yeah. So here I'm getting, let's go ahead and get, so rounding off this 3 significant digits, it's basically 9.78 meters per second squared. I'll just store that and use that number. So store 0. And then for the moon, we're going to get well, maybe that was the issue because I truncated it, but using
Point 62, right?
say again
1.62. Round
for
it up.
G for the
Yeah, for the moon. Yeah.
Okay, 1.62 meters per second. So then do the ratio and tell me what that is.
6.03.
Yeah. So you might have heard, but basically that's what we say is that the Earth is the gravitational attraction of the Earth is gravitational field of the Earth is 6 times greater than the gravitational field of the moon. So the ratio is 6. So we could write that something like this. So it's referring to field, not force. Although the ratio would be the same because they're just constant multiples, but that's really where it comes from. It's the comparison of field. So GE magnitude is equal to 6 times G of the moon, approximately. Okay. And did you calculate our forces, our gravitational forces on one another?
Not yet.
When you do it, let me know.
We have to use the Earth radius, right?
No. Oh, yeah, we have to do a distance between us. So let's say that, I don't know, if we're just standing by one another. So let's say 1 meter. That's a standard. That's standard thing.
Meter. Okay.
Yeah, 1 meter. 1 meter from.
Okay, because I was using the Earth's radius. It was really different number.
Yeah. Totally. Yeah. So just, like practical. So like if you're standing next to me. 1 meter. So let's see. So 80, 90, and then cone sheet. Yeah. So what I get is the force of attraction between us is like 4.8 times 10 to the negative 1, 2, 3, 4, 5, 6, 7.
Over -7, right?
Yeah, to the -7. So we could write that as newtons. So let's write that as, if you go higher, 1, 2. So 480 nanonewtons. So that's 1 billion times the force of gravity, the force of the attraction between two people standing an average, 1 meter apart, is basically 1 billion times, less than the force of the Earth, on the average person standing on the surface of the Earth. 1 billion times, 10 to the 9. So,
Well, now I'm curious. It might be a dumb question, Professor, but what's what prevents us from colliding? Is it ourselves or?
Okay, that's a good point. Calculate the average, like for when we're standing there, what is the average frictional force? Like say a standard coefficient of friction. It's a great question. US is equal to what? Like what's the standard? Like 0.2, 0.25, 3.3. No, static actually a little bit higher. So 3.5. Yeah, 3.5. Or what? Am I? No, what? 0.35. But am I drawing up like what's? I'm forgetting the order of magnitude. What's coefficient of friction? Is 0.3 or 3? It's 0.3, right? Right? Yeah, 0.3. So 0.35. What's the standard coefficient? Oh my gosh, I can't believe I'm just the semester. I'm like grading papers and things. Just kind of lost my 0.3. Yeah, of course it is 0.3. I just need to check on that. I'm questioning. 0.35 would be like a reasonable coefficient of friction between like 2 blocks of wood or something like that, right? Just sliding along, I think so. Yeah. Okay. So let's do like 0.35. Say US is 0.35 0. And the normal force, so the frictional force is equal to mu s times, so let's say I'm, less than or equal to mu s times the normal force. So well, we know that the frictional force is going to match that, but the maximum, in other words, the gravitational force has got to be equal to the maximum frictional force in order to overcome it. So the maximum static frictional force on me is going to be equal to mu s times my mass, which is times my weight, which is 800 approximately, if I'm 80. That's just approximate. So what we have is the gravitational force has got to overcome 0.35 times 800. And clearly that's going to be much greater, like 10,000 times greater, right? Because than this guy. So we calculated out, what is that going to be? I don't know, get math in my head. 800 times 0.35.
280.
Yeah, 280. So that's 280 times 10 to the 0. Okay. So this is 480 times 10 to the negative 7. So that's well, that's no, actually that's 10 million times. So basically the force of friction is 10 million times stronger, right? 1 million is 10 to the 6. So one more 0 is 10. So the frictional force on the maximum frictional force on my body that gravity would have to overcome to pull me towards you is going to be 10 million times larger than the gravitational force. So that's the answer. That's why I don't move when I'm standing a meter in front of you, because we know that the frictional force is always going to match it up to a maximum. So when you're pulling on me, the frictional force appears and it matches this force. But clearly it's got a lot of leeway, right? Because, it can go up to 10 million times much more force before the gravitational force would overcome that frictional force. I don't know if I'm explaining that well. I'm kind of tired. It's in the semester. I've been kind of doing a lot of stuff, so I'm scattered. But I hope that answers your question. I hope
it does. It does.
Yeah.
Thank you.
Yeah. In fact, as it turns out, gravity is the weakest force of all of them. It's weaker than electromagnet. We'll prove that next semester, but it's certainly weaker than the nuclear forces, strong and weak nuclear forces. And by the way, I think we've said it, but the strong nuclear force is the thing that keeps protons from spreading apart, because the protons are all attracted, all have the same charge, same polarity, and like charges repel. So if the protons are all in the nucleus close together, why don't they spread apart? Well, the strong nuclear force keeps them from doing that. Likewise, the electrons are attractive. The electrons are negative, and unlike charges attract. So why don't the electrons collapse into the nucleus? Because they're attracted to the positive charges there. Well, there's a repulsion force called a weak nuclear force. It's weak because it's much weaker than the forces that keep the electrons from imploding is much weaker than the forces that keep the protons from exploding. And so hence the weak nuclear force. And clearly those forces are much stronger than electromagnetic forces. And what we'll show next semester is that electromagnetic forces, well, the electrostatic force, I think it's about 10,000 times stronger than gravity. And we can easily calculate that with, we'll do that next semester. So, it's so weird though. Like, I think that must be a postulate that somehow the weakest universal forces seem to be the things that govern everything. Like when you look out in the universe, it's gravity is what we're so concerned about. And now we're looking for dark matter, which is supposed to be whatever, but still that's associated somehow with gravity. Anyway, it's so weird about that.
Professor?
Yes.
So when we are calculating the force between two objects, we won't utilize the negative sign?
No, the negative sign just tells you direction. So,
Okay.
I mean, you can, but it tells you the direction that force is acting.
Mm-hmm. So
I think you're... Go ahead.
No, go ahead.
I don't want you to overthink this thing. Like, it feels... I don't know how to... It feels like there's something about it that's bothering you or uncomfortable, and I don't know how to get to it because I don't really understand what it is. Can you explain a little bit more to me about why what it is about that minus sign that makes you uncomfortable or whatever, or makes you, because if maybe those are my words, maybe you're not uncomfortable, but something about it feels overthought, and I'm just trying to get to that.
I don't want to take class time. Maybe we can discuss it after class because I don't want to waste everybody's time. Today is the last lecture. So I'll ask you after class. That's fine.
Okay. I mean, it's not a waste because somebody else might be having the same question, but if I also don't want to put you on the spot if you want to talk, but I don't mind. I mean,
I just thought we would utilize it. We would actually use the negative sign to show direction. That's what I thought.
Let me give you a quick problem because we do actually use it, but it's just and you can kind of work on this a little bit. But it's a good question, actually. It's a very good question. Let me show you how you would use it. So let's say that we have, that gives me something to work with. Let's say that we have, so we just did this thing with me and Richie, okay, and he calculated my force, right? But what if there's more than one particle on me? So let's say that I'm here, I'm 80 kilograms. So mass 1 is 80 kilograms. Mass 2 is 90 kilograms. And mass 3 is equal to 100 kilograms. Okay, now 1, 2, 3. 1, 2, 3. 1, 2, 3. Let's put mass 1, mass 2 here at coordinates 2 meters and 2 meters. And let's put mass 3 at 3 meters down here at negative 3 meters and negative 3 meters. Now, the minus sign dictates, so I have to do a superposition, right? I know that the gravitational force of mass 1 on mass 2 on mass 1, so this is 2, this is 3, and this is 1. It's going to be in this direction. How do I know that? Because of that minus sign. So I've got one of two possibilities. If the force acts along the center of mass of both objects or particles, then I've got two relative options. Either that force can act toward mass 2 or it can act away from mass 2. The negative sign dictates that it's going to act toward mass 2, and that makes a difference in my final product. Let me show you how. Same thing over here. Away or toward? Well, it's toward. That's where the negative sign makes a practical thing. Because now, in fact, let me put a different color so that it helps them. So now I have to do the vector analysis. I want to find the, so for this problem, as a class, you can work on it, you know, at home, well, whatever. The question is, find the net force on mass 1. Well, now it's not just a matter of M1, M2 over R squared times G. I have to do that for both. That's going to give me the overall magnitude, but now I have to resolve those two vectors. In other words, F, I'll just call it F2. F2 is going to be equal to G M1, M2 over R squared, which is going to be, you know, you can, Pythagorean theorem, right? In fact, we could do it. It's going to be 2 squared plus 2 squared. Well, yeah, it's R squared. So R is the square root of 2 squared plus 2 squared, 4. So R squared is just 8. So over 8. And F3 is going to be G M1. So yeah, I guess you could put it in. So 90 times 80 for this guy. 90 kilograms times 80 kilograms. That's going to give me the magnitude of that force. And here, this is going to be G times 80 and 100. So 80 kilograms and 100 kilograms over 3 squared plus 3 squared, which is 9. So that'll give you those magnitudes. We can figure out easily what that is. And the angles for both is going to be 45 degrees because of how I chose it. So that's, so look, so what you're going to have to do then is you're going to have to get this component. That's going to be F2 times the cosine of 45. And I think the cosine of 45 is square root of 2 over 2. So I'm just going to go ahead and put that in. So F2x is going to be that F2 times the square root of 2 over 2. And so is the y component. I picked numbers I could easily kind of do. So F2y is going to be basically the same thing. F2 over square root of 2 over 2. And same thing with this. But they're pointing in different directions. So I guess what I'm trying to show you is that the whole reason, ultimately the fact that they're attractive forces and pointing along that direction, it dictates what these component directions are, you know, the directions of the components, what they're along. In other words, if F2 are pointing 180 degrees in the opposite direction, then this component would be, the x component would be negative and the y component would be negative. As it stands, those components are positive. That has to do with the direction of, you know, of the original vector, which is dictated by the fact that gravity is an attractive force and is pulling M1 toward each of those particles respectively. And so that's the only thing you need to know. I mean, other than comparing it, you know, directly to some other force, some other kind of force that might be in another direction. You know, like for example, in the case between me and Richie. So this is me, and we just calculated the force of attraction. So this is the ground, for example, on there. Right. I don't have any black ink anymore. I ran out of it. I ordered some they haven't gotten here yet, so sorry. So that's why I'm doing this. So, you know, you got like 2 people. This is one person. That's me. And so person 1, and then person 2. Well, as I was showing you previously with the masses, gravity is an attractive force. So let's just deal with this person 1. Person 2 is attracting person 1. So Richie asked me, why don't you just move toward that person? It's because the frictional force is opposing that. So the frictional force on the ground is opposite that. Right? I could draw from the center of mass, but whatever. So, you know, the minus sign is the fact that this force is pointing toward person 2. And that's it. That tells you how to know. Not only do you know the magnitude, but you actually know the direction because of the way gravity will always point relative to the essentially the source of the gravitational force. And that's it. That's the minus sign. But whenever we, yeah, that's it. Yeah, I don't know. Maybe I overdid it, but that's as much, that's essentially the value. So you could go ahead and finish this problem, right? You could finish it by calculating, you know, doing the vector analysis. You get the components, you add the components, and those directions were dictated essentially by the fact that gravity was attracted. Then you add the components to get the resultants of the components of the resultant, and then you add the components of the resultant together to get the resultant in the manner that we talked about. So yeah. Does that help at all? I hope it does. Maybe it was too much, or I don't know.
Yeah, I'll work on it more. Thank you.
Yeah, anybody else? Question with that? We kind of went past the break. I know it's last class. Let me give you about 10 minutes. Just take a 10-minute break. And when we come back, I'm going to discuss energy. Get into the issue that, the stuff that Amna was talking about. And then I'll try to get that really, kind of knock that out. And then I'll wrap it up by saying a little bit about Kepler's laws and showing some things. And then we can talk about a review. Yeah, so let's take 10 and then I'll be back. What time is it? Yeah, top of the hour, so I'll come back at 10 minutes. Actually, I'm gonna stay here and put in my name. Yeah. Let me give you a problem. Give you a problem here. This is a nice little problem. I want you to, let's say that we have a, let's do this problem. So it says that the orbital radius of the moon about the Earth is 3.8. Yeah, let's say that we know that orbital radius, 3.84 times 10 to the 8th. Now that, I guess that includes the radius of the Earth as well. I guess it would have to, yeah. So orbital radius, yeah. So assuming that, so here's a problem. Very nice practical problem that we already know the answer to because you already looked up the mass of the moon, the mass of the Earth. So this is a way to check it from a different theory, different concept. Assuming the orbital radius of the moon is, call it R, I don't know. Orbital. In fact, we should, so R moon orbit equals, what did I say? It's 10 to the 8th or something. 10 to 3.84. So 3.84 times 10 to the 8th meters. Use, now I'll just tell you what the concepts are. Step 5 in the problem solving process. Use Newton's second law, the concept of centripetal motion, universal law of gravity, to extrapolate or determine the mass of the Earth. So let me illustrate. So here's the Earth. Here's the moon. So this orbital radius is this distance. It's the distance from center to center. That's just, so make that assumption. That's our moon orbit. And assume a circular orbit, which is not really, but so a circular orbit. And then of course, then the speed of the moon around the Earth is constant. So assume a circular orbit and constant, basically a uniform circular motion. So that the only force on the object is the force of gravity. All right, so that's F of G. It becomes called a central force. It's the only force holding that object in, central force motion. So clearly it has, even though the universal law applies, the second law also applies, as we showed earlier. And all the things that we learned in motion, centripetal force, centripetal acceleration, all those things apply. So apply those and assume that you know the radius, this orbital radius. See if you can backtrack to figure out what the mass of the Earth must be. And then check that with the number that I gave you earlier. Okay, so do that right now. I get my tea here. So, did anyone make any progress at all with this? Richie, what about you?
Just a bit. I got the formula as A equals GM divided by RG.
A equals GM divided by R2.
Yeah, it's not the final. I think I still have to do something else.
How did you start?
Told us to go with Second's law, so that's F equals MA, and we have FG equals G times M over R squared. So I just placed the relationship as F equals MA, and I placed MA equals GM times M. over r squared.
So let's follow this. So net force equals mass times acceleration. That's right. What type of acceleration is it?
It's uniform.
Well, centripetal acceleration. It's uniform motion, but centripetal acceleration. Did you get that? So yeah, and the only force on is the force of gravity, Fg, right, equals M. But this is MAC. Remember that? So then you put in Fg, right? That's what I understood you to say. So you got G, and let's say this is the mass, the small mass is the mass of the moon. So M, MA, and M, M. So I want to make that AC now. So then G, mass of the Earth, and mass of the moon over this distance squared, r squared. Okay, got that. Equals mass of the moon times AC. Now, what did you do after that? That's where I got a little lost.
What I did was just place the F equals MA, and then MA equals the formula that you gave us, G times M over R squared. And that's what I stopped.
Okay, so that's, okay, cool. Well, we can see that these masses, the mass of the moon will cancel out, right?
Oh, yeah. Yeah, I see that.
Okay, so let's cancel that out. And yeah, I think you also forgot, or maybe missed that. Again, when I asked you what type of acceleration it is, you said, uniform motion, but this thing is going around in a circle in a uniform. It's the velocity is uniform. The speed, like V, is constant, but that's uniform circular motion, and that has a certain type of acceleration, right? Remember that?
Oh yeah, and the acceleration is pointing towards Earth. Yeah.
Yeah.
Centripetal.
That's centripetal. And what's the? How do we relate that to the speed? What's the formula for centripetal acceleration in terms of speed?
The one that it's no, that's the acceleration. I was thinking of V squared over R.
Yeah. AC is equal to V squared over R. That's right. So we can use that here. Might not be obvious, but yeah, so AC equals V squared over R. Right? Now you don't know the velocity, the speed of the moon, but you can extrapolate it because you know the period of the moon. It takes 24 hours, 30 days to go around the thing. So we could extrapolate that. So look, so that's why I didn't tell you this, but yeah, I was hoping you make some progress and figure that out. So we'll substitute that in. So we got G ME over R squared equals basically V squared over R. Now that's the same R. That's the radius of curvature, radius of evolution of the orbital radius. So I think I can go ahead and cancel one of those out. Actually, maybe I won't do it just yet. I'm not so sure about that. But let's go ahead and, so here we're trying to get the mass of the Earth, right? And so basically we have two unknowns at this point. That's what we don't know. We kind of just traded out one unknown AC for another unknown V. But we do know the period. The average period of the moon around the Earth is a month, right? And we know there's a relationship between speed and period. That's something that we did back then. So that, the velocity is equal distance divided by time, but the distance is the circumference, right? V, I think this is the formula, I gave you this formula back when we were doing that. Circumference over R, but that's equal to 2 pi, so distance divided by time, but the time is the period. So the circumference over the period, which is 30 days. So 2 pi, circumference is 2 pi times the radius divided by the period. So if V is equal to that, then V squared is equal to 4 pi squared R squared over the period squared. So now I can substitute, let's call this equation 7. I can substitute 7 into 5. So why don't you go ahead and do that and see if you can finish up and find an equation for M, and then find an equation for M, and then come and put in the numbers and calculate that and compare it to that number that I gave you earlier, which was, what was it, 5.67 times 10 to the 24th kilogram, something like that, 5.97 times 10 to 24. And tell me, go ahead and finish that and tell me what you get. Amna, you want to tell me what the analytical solution is? Did you get one?
What I got is M equals 4 pi squared over T squared, and the whole thing divided by R cubed.
Divided by or multiplied by?
Sorry, multiplied by.
And then also, what about the universal constant? That's still there, right?
Yeah, the G, right?
Yeah.
So it's
Good.
4 pi squared over G times T squared, and that whole thing multiplied by R cubed.
Gotcha.
That's what I got
Yes.
from M.
Awesome. So that is what I get. And so go ahead and plug in the numbers and tell me what the value of M is then. I'll finish out here. Good.
Professor?
Yeah.
I don't know if I'm confused. Shouldn't the pi in equation 9, shouldn't it be squared?
Oh, yeah.
Okay.
Sorry. Yeah. Now you're going to have to convert, you know, the period to seconds. So there's 3,600 seconds in, there's 60 seconds in a minute, 3,600 seconds in an hour, and 8,000, so that times, and then 24 hours in a day. So that's like 8,000 something. What? So 86,400 seconds in a day. And then times 30 days, right? Yeah, then times 30 days. Okay. And then you got to square it. I'm doing this right. So then you have to square that. So that's 2. Okay, what we got here? Oh, got the right order of magnitude, but something seems a little off. Probably that factored in that. Yeah.
What value did you get, Professor?
I got 4.98.
Yeah, that's what I'm getting to. I'm messing up somewhere.
Well, I don't think so. I think it's significant. These numbers that I'm getting, you know, they're average values. First of all, this is an approximation because the orbit of the moon is not circular. So these are a lot of approximations. We're not going to get this exact values. And then also we're truncating the 6.7 thing here. Like that's why we didn't get exactly 9.81 also, because it's approximations, but really the order of magnitude is important. So You got times 10 to the 24th, I'm assuming, right? I mean, we can actually calculate a percent like error maybe. But let's do that. So what we're getting here is 4.98 times 10 to the 24th kilograms. And what did I tell you? 5.97. So let's calculate a percent error. So you use 5.97, that's a theoretical. Yeah. It's like 17%. Yeah. I mean, it could have been anything in there. It could have been, it's the most likely error is this number here, the radius, because, you know, the orbits are elliptical and it's in the circle, but, you know, same order of magnitude. So that shows you that kind of things that we do to calculate these things. Yeah. Yeah. So everybody got that? We'll just take this as the answer. Understand what I'm saying there? It's approximation.
Yeah, I got 4.98 as well.
Yeah, cool. Now, this problem is a little nice. Something's come up in this equation 9. Equation 9 is quite significant because it actually leads to one of Kepler's laws. Let me solve that equation for the period. It leads to Kepler's third law. Can someone look up Kepler's third law, either Google it or look in the book and tell me what Kepler's third law says?
It says T squared equals 4 pi squared over GM of the planet and the whole thing times R cubed.
Yes. So that's not, are you reading the formula or are you reading something?
Oh, I was reading the formula. Do you want me to read what it says?
Yeah, I want you to get it from the book. Oh, it says that in the book?
Yeah.
Oh, yeah. Well, yeah, just read the qualitative description. Yeah, do that as well.
The square of the period T of any planet is proportional to the cube of the semi-major axis A of its orbit. And for circular orbits with radius R, that's the formula that I told you, where M is the mass of the attracting body. The sun is the case of the solar system. The sun in this case of the solar system. For elliptical planetary orbits, the semi-major axis A is substituted for R.
Yes, awesome. So let me do what she says, solve this equation for period squared. So basically I just cross multiply between period squared and the mass. And I'm going to put the constants together, 4 pi squared over G. I can throw the mass in there too. Put it under there, GM. Times, I'm going to separate this, R cubed. So a constant times R cubed. So Kepler's third law, in my own words, I'll say that the period of motion of the orbital body is proportional to the cube of the semi-major axis. In the case of the circular orbit, now what does that mean? Kepler's third law. The period, the square of the period. Now he did that. These people are amazing. Kepler was like 1400s. Basically looking up at these things, the moon and stuff and everything, and just mapping out the orbits. And over time, he traced out that they were ellipses. And actually Copernicus, I think, knew it, but he was scared to say it because everybody thought that the Earth was the center of the universe and he'd be killed and burned at stake for not saying that.
Yeah, that's right. I remember that from history. He was afraid because of a trial and he could have been executed by that time.
Yeah, the Inquisitions, yeah. So he published it on his deathbed. And because the only way you could figure it out is that if the sun was the center of the solar system, right? But then if that's the case, then the Earth is not the center, so what are you saying? We need to come pay you a visit, So, but obviously it turns out he was right, and then Kepler people followed up behind it. And Kepler then, took what Copernicus did and went further with it and published the laws. But literally these people, there was no theory. These people are just looking at the stars, mapping out the stuff and trying to figure out relationships. It's incredible. But the square of the period of orbit is proportional to the cube of the semi-major axis. Well, for a parabola, for a ellipse, it's kind of an oval shape, right? So like if, it's more kind of like this situation. So like if this is the sun, and this is a planet over here. So the sun is at one full side, there's full side, and then there's the other full side. But this would be like the Earth going around the sun, for example. Now this is exaggerated. It's not quite an ellipse like this. In fact, the ellipses are so slight, they almost look circular. But I'm exaggerating here. But just for the purpose of pointing out the semi-major and the semi-minor axis. So the semi-major axis is the long, the long side from apogee to perigee. So, and the semi-minor axis is the short axis. All right. Yeah. So it's actually this distance here, right, is a semi-major axis. It's a cube of that distance. But the interesting thing if you approximate a circular orbit, then the semi-major axis and the semi-minor axis are the same thing, which is just the radius of the circle. So in that approximation, it reduces to this formula here. And so the significant thing about this is that we didn't use, Kepler's laws, they don't really come from theory. They're just kind of postulates based on his empirical observation of his data. And you really couldn't prove it until Newton came along and gave us the Newton's laws, because we basically used two of Newton's major laws in this formula to derive that equation. The second law we started with, and then the universal law, which are separate laws. They're completely independent of one another, which is marvelous. And with very simple algebra, not even calculus, we could derive Newton's Kepler. So it validated Kepler's laws, which at that point was a 300-year-old law. Isaac Newton did this thing in 1720, 17 whatever. And Copernicus found this thing in the late 1400s. And then Kepler came along in the 1500s. So you're talking 200 years. Think about that. 200 years, from today was like, before the Civil War. In 300 years, 250 years was 250 years was approximately when this country was formed, right? 1776. That's like 250 years ago. That's how the difference between Isaac Newton and Kepler. So, basically, Isaac Newton took us out of the Middle Ages. So while I'm at it, I'll just go ahead and write down the other two laws, because they're not really, I guess we could prove the second law, but it takes a lot more. That's what I want to do. But, the second law says that a line from the sun to a given planet sweeps out equal areas in equal time periods. That's an artifact of conservation of angular momentum with this thing. So let me say it again. A line from the sun to a given planet sweeps out equal areas in equal time periods. That's the third law. Second law, and I'm going backwards. I don't know how this dude figured this stuff out. I don't know how. These people are amazing. Without calculus now. It's actually easy to prove it with calculus. Isn't that something? That's saying something. It's easy to prove it with calculus than to do with algebra and trigonometry. I don't know how you figure it out. A line from the sun to a planet sweeps out. These people are amazing. So going to this picture here, what it's saying is this. Let's say I take a line from this guy. Now, you know what happens, apogee and perigee. Apogee is the farthest distance away, apogee. And the perigee is the shortest distance away from the sun, perigee. I don't know if I'm spelling that right. I think it might be perigee. Yeah, perigee. Let me check that spelling. But because if it's a circle, then it's uniform circular motion. But in fact, orbital motion is not uniform because of the ellipse. So it travels slower, farther away from the sun than it is closer. In fact, at the perigee is the fastest speed, tangential speed that's moving, like something like that. And at the apogee is the slowest speed. Let's say if we're going this way. So if you could see the motion, it's kind of like it whips around the sun. So boom, and then slows up, really slow, and speeds up. So that's what orbital motion looks like. Okay, I think you probably knew that. Now, that's what can make this true, because what it's saying is that if you take a line and draw it from the planet to, to the sun, and we can do that a couple times, right? So like here, do that here, and then maybe do it when the planet was here, someplace, and then over here, someplace. Now we're doing it in such a way that the time it takes to go from, so these delta t's here are the same. And they're going to be more, the path will be different because it's going faster along, the average velocity along that path is faster than the average velocity along this path, so delta t. And out here, in the same time period, it might, it's going slower, right? So it might be something like, in the same time period, it's not going to cover as much distance. So it might be something like that. Right? So the arc length along the triangle gets larger, but that makes, and also you're farther away. So the point is that if you trace out equal time period and you calculate the area of this space, as long as you have equal time periods, the area will always be the same. The area will always be the same. And I could prove it, but it's a bit of a derivation. But it's essentially an artifact of the conservation of angular momentum. Why is this true? And again, when Newton came up with calculus and his physics, then you could prove it. So it's another thing you could prove. Conservation of angular momentum. Now, what is the criteria that angular momentum is conserved? What is the criteria that angular momentum is conserved? Come on, folks. Brian, what's the criteria? Richie?
Is it when the external force is zero?
That's
In that
linear.
external force.
That's linear momentum. Linear momentum is conserved. I'm not going to shot.
Is it when the the angular momentum at initial time equals the angular momentum at final time?
Well, that just states the conservation theorem. That's what it is. But I mean, how do we know that it's true? The criteria. So that is the definition of the conservation of angular momentum, that the initial and final momentum, angular momentum is the same. But what is the criteria that makes that true about for
Or when the net torque is zero?
Wonderful. When the net torque is zero. Awesome. Now, is the net torque on this system, the net torque on the Earth, is it zero as it goes around? How, and if so, how do you know? Can you prove it to me? Like show me how? Anybody? Not just anybody. I just told you that angular momentum is conserved, so clearly the net torque must be zero. So talk to me about that. What is there a torque on the system? What forces are on the system, and how do we know about a torque? Like what did it have to do with anything? Like what force is on the system, and what's the direction of them?
Well, could it be the attraction between the two bodies?
Yeah, it's the gravitational force. When the Earth is let me draw another picture.
So they apply each one's forces, and that's equal due to the third law.
Well, yeah. Well, let's focus on the Earth. All right. So is there a torque on the Earth as it moves around that thing? What are the forces on the Earth as it goes around? You just told me, right? Gravitational force. Let's say this is the sun here. Put a dot. Sun. Here's the Earth. The direction of the force on the Earth at this point is in toward the sun. Right, as gravity acts along a line between the center of the bodies. So that's the gravitational force Fg. Now, R is the unit, is the position vector that defines the position of the object from the axis of rotation. Clearly, the center of the sun is the axis of rotation, right? So this is R. Pointing from the sun to, because like my origin would be, my axis, I would place it here if I were kind of analyzing the problem, right? So my R vector points from, so it goes right on top of the force. So this is R. What is the equation for torque? Torque is equal to R cross F, which is equal to R times F times the sine of the angle between R and F. What is the angle between R and F? What is it going to be always, no matter where the Earth is on its orbit? Brian, what is the angle between R and F? R points from the sun to the Earth, and the gravitational point is the central force, so it points back toward the axis of rotation, the F. So what's the angle between R and F? Richie, what's the angle between R and F? Amna?
Is it 0 or 90?
Which one?
So where is R and where is F? Can you?
Yeah, so this is the Earth.
Mm-hmm.
Gravity points back toward the sun, right?
Yeah.
And so F is the purple. Can you see the purple vector?
Yeah.
Okay. And, you know, when we measure something, we place our axis at the axis of rotation. So if I were to, I didn't really draw it very carefully, but like if I placed an axis to measure the position of the sun, of the moon, of the earth, it's from, you know, we generally, the axis of rotation is through the sun. So I've placed my axis, I've centered my axis at the center of the sun. So then any vector that I use to determine a position is going to point away from that. So R is pointing toward the center of the earth. So that's the direction of R.
Mm-hmm.
So what is the angle between them?
90.
I don't see how you're getting 90. How are you getting 90? Let's use my crayons here. I mean,
The angle between R and F would be 0, but previously we worked with like, because then that would make the force like the whole thing 0, because sine of 0 is 0.
that's true. And what's wrong with that?
So,
But that's not the
oh yeah,
angle.
because net torque is 0. That's right. Okay.
Yeah, but that's not the angle. The angle is not 0. That's the direction of the force, and this is the direction of the R. So what is that?
180.
180. That's right.
Okay.
Good. Which still gives you what you need.
Mm-hmm.
Sine 180 is also 0, but it's important to get that right because you know it's
Yeah.
you know it's yeah. Yeah, so sine 180 is 0. So that's the only force. So the net torque is actually 0 on the earth. It's not, it doesn't have, so, you know, so angular momentum is actually conserved. Yeah. Angular momentum is conserved. So it's valid. And so, yeah. And so the final law, I'll just say that it's easy. Each planet moves in elliptical orbits with sun as a foci, it's just that. But again, that also can be verified by Newton. It's a much more complex thing. You have to get the equation of motion. You know how I've been like the equation of motion, like with all of these, like with oscillatory motion or drag force, I apply Newton's law and then you solve the equation. In other words, let me just write the law, then I'll tell you how you prove it. First law is that Kepler's law is that each planet moves in an elliptical orbit with sun as the foci. So each planet moves, basically orbital bodies move in elliptical ellipses with sun as a foci. So applying Newton's laws, you're back to that thing. So if the orbits are actually circular, then it's easy to solve it. We just did that. But they're not. They're elliptical. So you can't use centripetal force, motion, not in the simple formula that we have. Acceleration is a combination of centripetal motion and linear motion because the speed is changing along the path. So that it's not that simple. So in fact, going back to that equation, what we have is G M over R squared equals basically AC or A, the acceleration. But that A, you know, it's, you know, we can write it with dot notation, which I like to write. And that R is the second derivative of the, like this R vector, it's changing. it's changing its length and its angular motion, everything. So you have to use spherical coordinates and write, well, you have to think about R in terms of, you know, its derivative, dr d squared dt squared, where R is, I don't know, I guess you would use cylindrical coordinates. R, you know, like in rectangular coordinates, R is equal to xi plus yj plus zk, right? But in cylindrical coordinates, R is equal to, I guess you could say like R R hat plus phi, the angle that it's making with respect to the axis, phi hat, and then plus z. Z is the same coordinate. So you have to take, it's a complex thing. This is a three-dimensional problem. You have to take that all these things are time dependent. Well, z is not time dependent, but R and phi are time dependent. So it becomes a complex problem where you have to solve them independently. You have to break them up into their independent parts. And if you do that, you can apply calculus and get the differential equation. You have basically two differential equations. One in terms of R and one in terms of phi, and then you solve them. And when you put those two things together, you can derive the formula for an ellipse. It's a really complex problem for like junior, senior level physics. But my point is that Newton did it, and you couldn't do it without starting with the second law. So basically, Isaac Newton verified with his laws of motion and his universal law and with calculus, he was able to verify theoretically everything that Kepler had figured out empirically. So again, literally the man took us out of, and that and much more, obviously, you know. So he just took us out of the dark ages. It's incredible. It's incredible. It's just incredible. I don't know. Yeah, I'm not going to go on my soapbox about it. But anyway, those are the three laws. Well, yeah. I'd like to talk about that. I could say something about energy really quickly, but I'm running out of time. I wanted to talk about the exam. Since Amna asked me, how much time I got? Yeah, I'll take 5 minutes, 10 minutes to say something about the energy and show you where that equation comes from. And then we'll talk through a review. Whew, Lord. Well, let's make an analogy. So this is, make this as clear as possible. It's not. Gravity, when you're thinking about Newton's laws of motion, weight is mg and potential energy is mgh. How did we get that? How did we get that? What we did is we said, let's calculate the work done by gravity as something falls. And we put it in this formula. Work is equal to the integral, it's the definition of work, F dot dy. That's all it was. If F was mg, it was a constant. So the weight mg. So first of all, it falls along the same direction. Either, gravity is always down. So if it's falling down, I take the dot product, that's just the integral of F dy cosine of 0. Cosine of 0 is 1. So that's just the integral of F dy. But F is equal to mg, so that's the integral of mg dy. Mg are constants, so they come out. So mg, the integral of dy, what is that? That's just from 0 to h. That's just mg y from 0 to h, which is just mgh. And then we define that the work done is equal to the negative of the change in potential energy. And that's how we associated those. We said, okay, potential energy on the ground, we define that as 0. So the potential energy at high H, we define that as mgh. So how did we determine the potential energy function for the weight in terms of Newton's second law, mg? We figured out the amount of work that that force did. Then we equated that, we defined that as equal to the potential energy. Straightforward mathematics. Again, can't do that without Newton and calculus. Okay, we're going to do the exact same process but looking at gravity, the force of gravity from a different perspective, looking at it from the perspective of the universal law. And Amna, that's where you're going to get your equation from. That's where it comes from. We do the same thing. A little bit more complex integral, but not that much more. Still simple, but just a little bit more. And so, but it's the same process. We start with the work function. Work equals the integral of f dot dy. Now, in this case, we can maybe think of, let's think of like we have a mass out at infinity, like the moon or some orbital body, and we're bringing it in out from infinity because we really have, when we're dealing with a flat surface, we have to define the 0 potential energy point as the ground. But when you're talking about orbital bodies, that doesn't make any sense. It's just the surface of the planets. Why is one surface should be 0 on the other? Because the thing about when you're flat on the Earth is that no matter what the mass is, if it's on the ground, its potential energy is going to be 0. But when you're thinking about the universe and heavenly bodies, where is the most obvious place where every object in the universe, even black holes to stardust, where their potential energy is going to be 0? It's not going to be on the surface of any arbitrary planet. But there is one place where all of their potential energies would be 0, and that is infinity. So infinity is analogous to the ground for the universal law, force law. At infinity is where the potential energy of any massive body is 0. So if I have a mass like the Earth or the sun, whatever, and I want to figure out how the potential energy is, what it is, then I take an object and let it fall in from infinity. And if I do that, the direction that it's moving and the direction of the force of gravity is going to be parallel, so that that cosine of that angle will be 0, just like it was here. So I'm coming in from infinity, right? So again, you take the dot product. Now here is FG, capital G, but still the direction between them, if I'm coming in, just making the same analogy. I can go out too, but let's just come in. It's going to be, actually, you need to get that minus sign out of there. So technically speaking, we define Y as pointing out in that case. Because if dy is pointing in when I come to infinity, it means that the origin is at infinity. But we don't normally do that. We set up having the origin at the center of the planet. So dy, just like I did before. So dy is pointing from the planet, out to the object coming in. Like this is the axis. So like if this is some planet, some object coming in from infinity, it's the same thing we just did. So this is the mass in question, m0, and this is the position vector pointing to that object. And we don't use y, we usually use r, dr actually, because it's spherical or coordinates. So this is r. So in this case, r points from the center of the planet to the mass, but the mass, if I'm bringing it in from infinity, then it's the force of gravity on it is in the opposite direction. So, they're 180 degrees. That's the point. So the force on the object, again, is like this. Now, this is not torque. This is force we're dealing with. If it were torque, like we just did, it would be 0 because it's a cross product. But this is the dot product between F and R, between these two things. So that gives us a different result. The dot product, F dot dr, is going to be the integral of, it doesn't give a torque, but it does do work, right? So that is the integral of f g dr cosine of 180, and that pops out that minus sign that you're talking about. So minus the integral of f g times dr. But what is fg? Fg is integral of g m, small m, over r squared dr. The g's and the m's are constant, so they come out. All right, so then minus g m integral of dr over r squared. Okay, what is that? What is the integral of dr over r squared? What is the integral of 1 over x squared?
ln x, right? ln r.
No, that's the integral of 1 over x. Over x squared is easier. It just abides by the formula. It's just the formula. It's minus 1 over r. The formula for the integral of dx over x to the n is equal to 1 over n minus 1 times x to the 1 over x to the n minus 1. So in this case, two minus 1 is 1. So I'm going to get minus g m, and then I get
1 over r, right? Because it was.
Actually, I think I messed this up. It's that formula, but you know, it's
Because when you put the r squared like in the numerator, it's actually r negative 2. So when you integrate it, it's n, which is negative 2 plus 1, which will be negative 1.
Yeah,
so
negative
1 over r, right? I haven't done it. But
that's what I've written here. Did I write that wrong?
No.
Yeah, but it's 1 over r. Yeah, so you're right. By the formula, it's going to be a negative, because r to the negative 1 is actually, this is what I messed up. Yeah, it's this. Yeah, I don't have to. My bad. It's x to the n dx is equal to 1 over n minus 1, x to the n minus 1. My bad. Yeah. So when you do that, you're going to get a negative 1 out. So so there's a negative sign that comes out. So I'll just put that in parentheses. That negative sign is already there. So negative 1 and then 1 over r. And that goes from, so let's call this r1, and this is, because I'm going in, right? So this is r1 here. That's tough. So this position is R1, and this position is R2. So I'm going from R1 to R2, but remember R2 is less than R1 in this case, because I'm going in. So that minus sign will cancel, but then it's basically 3 minus signs that pop out of this. So when I put that in, I'm going to have G, M, the minus signs cancel, but then I have 1 over R2 minus 1 over R1. But that's a little bit deceiving, because R1 is, right, because the R2 is minus R1. Well, in general, because I also have to have it going out the opposite direction to a negative work. So in general, the way we write it with a negative sign. So we usually flip this around and bring the negative sign out so that we have a negative G over M. Because like if I were going in from infinity, then R1 is go out to infinity, yeah. I guess we generally write it like this, that we would have take a minus sign on and then R1 minus 1 over R2. Yeah. So in general then, well, no, I guess not because we have, yeah, so that's going to be positive. So the work done is
So the limits, I think you have the limits wrong. Isn't it? Because the book says R1 to R to infinity. That's the limit.
It doesn't matter, Anna. It depends on what direction you're going. With them, they went from R out to infinity. I'm coming in the opposite direction. So it still works out. This is not, I just did it this way because it's the way I think about it. Either way is fine, but you got to keep the minus signs in.
No, I'm just talking about the limits, like R1, either one of them should be infinity, right? Because you're coming in from an infinity.
They can be or they cannot be. It doesn't matter. Okay. I could come in from infinity, but in this case, I could extrapolate R1 to infinity. I can do that. You're right. I can do that. But I can also just come in from any place other than infinity. It's going to still give me the same, I can do that. I like to do it here. Then when I get the answer, then I can extrapolate and call the thing 0 out of infinity. But either way, I can start the integral from infinity or I can start it anywhere. But the point is, at infinity, the potential energy is defined as 0. But so look here. Let me finish this out real quick. So with this actually is correct because gravity is doing these minus signs cancel and I get positive work done. And the total amount of positive work that I will get done will be this. And this is a positive number in here because R1 is greater than R2, but I'm taking the inverse of R1. So this number is smaller than that number. So that whole thing will be a positive number, which is right. Because when I'm coming in, gravity is doing positive work on the object, right? It's moving in the same direction that gravity is pointing. So that's positive work as it comes in. So 1 over R2. And it's also consistent with what you said, Anna, because if I take R1 out to infinity, then this term goes to 0. Well, let's do this first. Let's do this. When we have to put it in terms of potential energy. Now I still have to finish this part where I equate the work done to the change in potential energy. So the work is equal to the negative of the change in potential energy. Technically, that is the potential energy, the negative going from its final minus initial, right? So it's minus U2 minus U1 equals this thing here, G, M, 1 over R2 minus 1 over R1. Okay, so if I take doing what you just said, here's where I put that in. R1 is infinity, so that goes to 0, and the potential energy is defined as 0 at infinity. So what I end up having then is that the potential energy at my point in question at UR, so 1, 2, 3, 4, 5, 6, 7, and then 8, I would say that U of R, at minus sign, I'm going to take it back over, is equal to a negative G M M over R2, which is just some arbitrary R. And that's why that's the formula that you were asking me about. That's where it comes from. And this is a definition. We define it as such. We define the potential energy to be 0 at infinity. And therefore, with this derivation, when we put that in, then the potential energy at any point, a distance r away from an orbital body, the potential energy is negative GM M over R. which is quite significant because of the way we define potential energy. It's saying that the potential energy of any orbital body is actually negative. Is negative. And if we were to graph it, potential energy U of R with respect to R, it looks like this. It goes, as we get closer to the object, it goes to infinity, and as we get far away, it goes to zero. And it's negative, so it's on the opposite side of the x-axis. It's like this. So two significant things about it. It's not like the force. The force goes as a 1 over r squared. So it goes as 1 over r, which is this curve, and it's negative. So it starts out at negative infinity and goes to positive, goes to positive infinity goes to zero as r goes to positive infinity. That's characteristic of potential energy function.
So how would the graph of force look like?
The graph of the force is 1 over r squared. Very good question. Force is 1 over r squared. It looks like this. Now, it's an r squared, so don't confuse them. It's more like this kind of thing. It's a sharper curve. So when you get close in to the object, it starts to go up to infinity. And it's not defined at the center. Like if I take this mass and I bring it into the center, the force on that object is not defined at the center of the object. But as I move away from it, in fact, when I get inside, it becomes, in fact, it's zero, my bad. So yeah, let's do this. If you graph the force law, that's something like, so let's say that this is the radius of the Earth. And this is the, so I was a little bit wrong about that, I forgot. So this is the radius of the Earth. From infinity to the surface of the Earth, it's the force law that we were talking about. It looks something like this. And so that's 1 over r squared. 1 over r would be something more like this. So it's definitely a different. 1 over r would be something more like that. So that's 1 over r squared, okay? Looks like a 6. So. But I'm not going to infinity. I'm not going all the way to the center. It would really do something like this. Go to the surface of the Earth, because it's clearly not infinity. My weight is not infinity, right? I'm on the surface of the Earth, and I'm at the Earth's radius. Now, we're not going to have time to prove this, but there's a law called Gauss's law, which I don't have time to talk about. We'll talk about it with the next semester because there's one for electrostatics. You can use Gauss's law to actually, you could use both universal law as well. It's just longer and harder. But you can figure out, it turns out that inside the Earth, the attractive force is not 1 over r squared. It turns out it's linear. It's proportional. The gravitational force inside a body is proportional to the distance you are away from the center. And it becomes a linear function. And as you go down from the surface to zero, assuming a uniform density, it's linear. So at zero, it's just a line. So at zero, the weight is zero, which makes sense because you should be weightless down at the center of the Earth. So the force of gravity is zero. And so if you graphed the gravitational function of the Earth from the center of the Earth out to infinity, it would look like this. It would be zero at the center of the Earth. It would go up to a maximum value, which is your weight at the surface of the Earth. And then as you move away from the Earth, it drops off as 1 over r squared, and it doesn't get to be zero until you're out at infinity. So this would be the graph of the, of the force with respect to distance. And this would be the graph. Actually, I have to do something a little different. Like inside the Earth, it's going to be different as well. So is that right? I have to think about that. Potential energy function. Inside the Earth, potential energy I'm drawing a blank actually. Yeah, I'll have to come back on that. I can't remember. On a blank. But that's the equation. That's the function for the force. Yeah. So the upshot is that the potential energy is negative, and turns out the total energy is also negative. I'm not going to show that. I'm going to let it go right there. But so when you're thinking of on the surface of the Earth and Newton's laws, potential energy is mg y or mg delta y. When you're thinking about two bodies, heavenly bodies, we have a different form of the equation. It's negative. Universal law of gravity, the product of the masses divided by the distance between those center of those two bodies. Oh, man, well, yeah. So that's what that equation is about. So that's what I was telling you, is that that negative sign means something different for this formula because it's a scalar function. It's energy. Energy is not a vector. With the force, it's opposite direction. With potential energy, it means that the gravity does negative work. It requires it's how we define the energy as negative. And the way you want to think of it is this: gravity is doing positive work, but really what happens is it's like if you had some universal being who plucked the object off of. So you know how this is the way to think of it, and we'll let this be the last point. Whenever and take this in because this is going to work. This is really the way to think about it. Let's think about me picking up an object off of the ground. When I pick it up, gravity is doing negative work, essentially, right? Because it's going out. But the potential energy that it has is actually going to be the energy, the work that I did on it when I picked it up. Because I'm doing positive work. My force is in the same direction of motion. And when I pick it up and it's at that point H, well, if you calculate the work that I did, it would be mgh based on the way I showed you earlier. Gravity is negative mgh, I'm positive mgh. But they don't cancel because there's work of the friction, like it's, work is being, basically the amount of energy that I'm putting in the system is equal to the work that I do on it. So mgh is going to be the work that I put into it, but that also would be defined as the potential energy that it has when it's at that point. And it's positive mgh, right? Because I did positive work. Okay. That's why the potential energy of the object is positive, because based on how I define the zero potential energy point and the work that I did relative to that zero potential energy point. Now, let's say that this wall is infinity and my fist is the Earth or some orbital body. Essentially, what you're doing is we're defining now zero potential energy is this point. But gravity is not from, like in this case, the gravitational force was originating at the same point where you define the zero potential energy point. Here in this example, this is the zero potential energy point, but the gravitational force is in the opposite direction from, relative to how you defined it before. So what's going to happen in this case, when I'm doing work, I'm not doing positive work. I'm doing negative work. Why? Because in this problem here, I picked it up at a constant velocity. So I'm at every point, I'm working against gravity, right? But the forces are equal and opposite. In order to pick it off. But in this problem, basically, I'm pulling on the object to keep it from accelerating in. But the direction of my force relative to the direction of the motion that it would go is opposite. I guess, yeah. Yeah, I just kind of lost my train of thought. Yeah, maybe I should have focused on gravity, actually. The work done by gravity when I'm going up. Because I'm working against it, but yeah, it's hard to. No, it's just when I take it off take the thing off of infinity and bring it in, I'm doing negative work because I'm pulling in the opposite direction as this thing moves in. Yeah, that's the difference. Here, the direction of my force is in the direction of motion. But here, like the direction of my force is back in the opposite direction. And if I let it go, it would accelerate in the opposite direction. So I'm not actually like I'm doing negative work because my force is in its opposite direction of motion as it moves through that distance. So when it gets to the point where I want to place it, the work that I've done is negative. And so when I evaluate that, when I define that in terms of the potential energy that it has, the potential energy will be negative because I basically did negative work on it to get it to that point based on how the zero potential energy point is defined relative to the origin of the gravitational force that I'm working against. So, and that's always the case with any kind of orbital body, and therefore any orbital body will always have the potential energy of any orbital body will always be defined as negative. Yeah, that wasn't a very good explanation, but it's the best I can do at this point. I'm just tired. Yeah. So that's it. That's a big deal. That potential energies of orbital bodies is defined as negative, and this is the functional form. And we get that from a combination of Newton's second law and Newton's universal law and the definition of work on the object to bring in that object from infinity. Okay.